Okay, yeah, hi, Walter. I was just about to ask you that. All right, so welcome back, everybody, to second or third day, really, of online to 11. Um, hopefully, recitation was useful yesterday and went okay, or have to go through all of your feedback that hopefully you've left or will leave soon on the on the Blackboard reminders. Okay, so we did want to record lectures for people who can't attend live because of time zones or whatever. Um, and it turned out the Blackboard Collaborate recording was really not super useful because it only shows you like one thing at a time and the chat is not synchronous. So probably your best bet if you want the videos is the YouTube channel, which I linked there. And actually, I didn't have the link available when I made the slides, but we're working on getting these uploaded on this other website for those in China, which I think there's more information on the website already, our website already. And again, so saying I'm disconnecting or something. Okay, we'll see if that's. Yeah, okay, am I back? What, did I cut out in the middle of what I was saying? Well, I was basically just reading the slides that are up. So yeah, I saw it go crazy for a bit. So yeah, YouTube channel, Walter put it in the chat there. The Bilibili, I guess, is going to have it for those in China. And I think we're going to try to break it up a bit so it's not all 1 hour and a half video on YouTube going forward. Also, so go ahead and again, remember about the recitation journals for participation credit. We do want you to work on the recitation materials. It's probably the most important part of the class. And it's best if you work with someone else, whether that's live at the Blackboard Collaborate sessions, or if you make your groups offline, that would also work. Working by yourself should be a last resort, basically. But if you check the Blackboard recitation tab, you should see that there's an assignment to say what you did for recitation. So for instance, the one for Wednesday should be up and you should be able to see it. We decided yesterday with all the craziness to extend the homework 9 due date till end of day today instead of yesterday to give you a little bit more time. And again, I'm not going to go through all the info on changes to the class. We talked about that on Tuesday, but all that should be on the website if you still need to go back and check it. Okay, any really important questions about the class before we get started for today? Okay, so I just want to say, basically, in case you were worried, because I know some people have probably felt like they're falling behind a little bit, for this section leading up to the third exam, we've basically already introduced everything we need to know. So hopefully that actually puts you at ease a little bit. So starting today, it's really about putting it all together into a structure where we can think about how to do problems and start to do maybe problems that are a little bit more complicated with maybe more than one step. And we'll continue to work on this as we go through next week, right, leading up to the exam. So there's nothing new. We've talked about momentum. We've talked about energy and potential energy, right? And so now we're just trying to put it all together, right? And so our goal for today is really just to explore how we can use conservation of momentum and energy to understand a bunch of different kinds of problems. And they all sort of share the same idea that they're about something, a situation before and a situation after some process. And the process can be really complicated, and we don't want to try to understand it because that would just be too hard, right? The forces involved are just big and they change really fast in time, and it's just too hard to try to sort it out that way, right? but we can understand what's going to happen from before to after using these conservation laws, right? And so things like motion with conservative forces, right, or collisions or explosions, or something else, all of these basically are going to work the same way, right? And we're going to use the same ideas to try to understand them. And so this is much simpler. And yeah, this can be very difficult at first because it's going to seem like we're seeing a lot of very different situations, very different things happening, right? But what we're going to try to build from starting from today is really a framework where we can think about them all in the same way. Okay. So I'm going to start with the first pre-lecture question. This is an interesting one, and I did this one the last time I did the class as well, and it was interesting to see how the answer changed. In that fact, more people went for the correct answer this time. So it's about a what seems like a very simple situation, right? So a ball is bouncing off the wall of a room. And we said this very specific thing, right? That the system that we care about looking at is the ball, right? And so just a simple question, is momentum conserved when the ball interacts with the wall? And so the right answer was no, but only about half the people that answered got no. So I wanted to break this down a little bit more, right? So let's look at a picture of this, right? Before, the ball has some velocity towards the wall, and I'll go ahead and say that positive direction is the one to the right. Yeah, are other people up to date on slides? So I should be on 5 at the moment. Let's try this. Yeah, no, I got the message. I'm trying resharing to see if that works. All right, let's hope it stays okay. You know, let me just go check on something real fast. Okay, I wanted to make sure that they weren't using too much of my bandwidth. Okay, so slide 5. Okay, 4, if you didn't see it, was the pre-lecture question. So it was about 50-50 on the pre-lecture, whether momentum was conserved or not. And I went ahead and gave you the answer that it's not. But let's think about this. So slide 5 here, the bouncing ball before and after, right? So before, it's going towards the wall with some velocity. After, it's going away from the wall with some velocity. And let's go ahead and say that towards the wall is positive direction. So in this case, if the system we care about is the ball, the question is that I want you to answer here is what are the initial and final momenta? So right, initial is before, final is after, right? Before it hits the wall and after it bounces off. So geez. All right. Got the poll up. Okay, so why don't we just take a few more seconds on this one? Just still waiting to put in a response. All right, 3, 2, 1. Right. All right, so vast majority of everybody who responded said C, right? So C, well, yeah, that's right. Right, and so just think about it. That's an obvious way to see, right, that the momentum is not conserved, right? It's different before and after, right, because it changed direction. Now we can see this from a more fundamental aspect, right? We were going to say that momentum is not conserved because there's a net external force acting on the system of interest, right? So in this case, the wall is pushing on the ball when they come into contact, right? And this gives it that impulse that changes the momentum to go the other way, right? And even if, like in this poll question, right, the force leaves the object with the same speed, right? If it changes the direction, then the momentum is still not going to be conserved, right? Because momentum has both the magnitude, right, the mv, and the direction. All right. Another question. So the same setup with the ball. Is the kinetic energy of the ball the same or after the collision? Okay. Oh, there was a hand up. Now it's down again. Okay, why don't we just take a few more seconds? Almost everyone's responded. Okay, so 3, 2, 1. All right, so about 2/3 of the people are saying that they think that it is the same, right, after as before, but there's about 1/3 of people that say that's no. And unfortunately, it's really tough in this format for us to do the usual thing where we sit and talk to each other at our seats, which is kind of a drawback of this format. So I have to kind of do this. We have to think about, okay, is it yes or no? So, well, what is the kinetic energy of the ball, right, before and after? So it was going the same speed, right? It's just going in a different direction, right? And so the kinetic energy is just 1/2 mv squared. And if it has the same magnitude of v, right, you get the same v squared. And so you do get the same kinetic energy, right? And so the people who answered A were right. Right? Kinetic energy doesn't care about direction. Right? It's just about the magnitude of the speed that you have. And in particular, as we start to do problems that even involve both x and y, so they're not all in one direction, there's really only one energy. It doesn't care at all about direction, not plus and minus, not x and y. Right? It's always just about the total motion that you have for kinetic energy. Right. In this case, like you can, it's tough to see like from question is, are we assuming the wall has infinite mass? That's actually a really good question because in some sense we did that very implicitly because I told you the ball bounced off with exactly the same magnitude of momentum as it went in. So it came out with the same speed it went in, right? Which means that essentially the wall does have to be infinite and can't move. Yeah. So it's an ideal wall, basically. Normally what happens is there would be some like literally unmeasurably tiny change in the momentum of the ball. So it would be in the magnitude of the momentum. So it would slow down just a little bit, and the difference in momentum would be picked up by a very, very tiny momentum absorption by the wall and the earth that it's connected to. Right, and that's actually why I was being careful to say that the kinetic energy is just the same in this case, because I was mostly just talking about the direction. So the conservation of kinetic energy in this case is not so obvious. It would have to be that I told you, oh yeah, you have that it's an elastic collision, basically. Okay. Right. So what I wanted to do as we go through the lecture today is we want to break down all these different questions we could ask about that energy conservation, and look at them through different examples, right, where we can see what's going on. So the first one on here was, is energy, so basically we want to start asking the question, is energy conserved, and how do we know that when we're doing a problem? Right, and so the first one I put on there is, are the only forces that act conservative, right? And if so, then yes, energy is going to be conserved because we're actually going to account for that energy via the potential energy that's associated with those forces, so like the gravitational potential or the spring potential, right? And so here's another question for you to think about. Okay, so if you want to throw a rock off of a bridge, so you only have so much arm strength, right? So if you go to make a throw, you can give the rock so much speed. Now you can throw it in different directions. And let's say for the sake of argument here that you always release the rock at the same place. So I don't know, maybe if you need to throw it down, you need to get on a step stool or something so you're a little higher, and so the rock leaves at the same place, right? So let's say you release the rock always at the same height, and you always throw it with the same speed, but you can choose which way you want to throw it, right? You can throw it up, you can throw it straight, you can throw it down. And so the question is, which way should you throw it if you want to make sure that the rock has the highest speed possible when it hits the water? Okay, see, almost everyone has responded, so let's just take a little bit more to think about it. All right, so let's stop this in 3, 2, 1. All right, so a lot of different opinions on this one, right? So we got almost equal. The most common one is doesn't matter, but then also very popular, both angled up and angled down. Okay, Sam, did you want to say something? That's what I'm taking the hand raised to mean. So you should be able to say something now if you want. Okay, or maybe not. All right, we'll go back. All right, so since we have a lot of different thoughts on this, let's try to direct a bit how we think about this. Okay, so how about think about a different question. So first, yeah, okay, air resistance. So right, we decided just to ignore air resistance here. Again, it just makes things more complicated, and we're trying to get the very fundamentals down. Okay, so is the energy the same or different in each of A, B, and C at the beginning, right after it's left your hand? Right, think about that. Right, so it's at the same height. They're all going the same speed. Right, and as we just saw, right, it doesn't matter which direction something's going for its kinetic energy. Right, so the energy is the same, right, at the beginning. What about at the end, right? So the height changes, right? But the gravitational potential energy, right? Gravity is the only force here, right? Once it's in the air, because we're ignoring any air resistance. Gravity is a conservative force, right? So any work that it does is just moving the energy from the potential into the kinetic energy, or vice versa. Right? And so by the time you get down to the water, gravity has added the same amount of kinetic energy no matter what path you take. Right? And so that's why the answer is that it doesn't matter, right? Which is the most popular. And this is really showing you why it's important to think about things in terms of energy, right? If we go back to doing like the projectile motion like we did in the first part of the class, right, then it makes the problem more complicated in some sense, right? Because you have to think about, oh, okay, well, what speed do I get, right? And we saw this when we did projectile motion, right? We actually would see that in the parabola, you would get the same speed on the way up and the way down, right, when you're at the same height. Now, we didn't talk about it at that point in terms of potential energy, right? But now we can think about it that way, and it actually helps to simplify things for us a bit. Right. And so the only difference would be between different ways you throw it is like the exact little amount, right, that it changes maybe the height that you release the rock. Yes, that's a very good question. That would the speed and x and y components be different for each way? They would, right? Depending on how you throw it, it can change the angle essentially that it hits the water. It's just that the speed, right, the magnitude of the velocity, right, which has both x and y components, the total magnitude is always going to be the same because the kinetic energy is the same. Right? But you can change the angle. Right? Because if you threw it up and then it went like straight down, right, it would be more in the y direction, right? And then if you threw it straight out, you're giving it more x velocity. And like just like in projectile motion, we learned, right, that gravity can't take away that x velocity. It's going to stay the same the whole time. Right? And so since now you have more x velocity if you throw it straight ahead than if you throw it up, then you're going to have less y velocity when you throw it straight ahead when it hits the water than you do when it's thrown up. Okay, actually, Walter, if you're recording, this probably would be a good place for a cut. And then the next one, we're going to do a more detailed example. So.